All right, welcome to lesson 7.2. This is the last lesson in the course. We're going to do area moment of inertia. So we're going to take a break from forces and things and go back to geometry. Remember, we did some centroid calculations there a while back to help us with our statics. And this is the same thing. It's very related to centroid. It's kind of the next step beyond centroid. And it also is going to be used later in more work that you would do with statics and mechanics and materials and other courses in the future. So we're not really going to do much application of this into statics per se, but this will be a springboard for you to move on into future courses, knowing how to calculate the area moment of inertia. Our objectives: we're going to learn how to determine the moment of inertia for an area, for like a simple area, using tables or by integration. If it's a function, we can integrate and find the moment of inertia. If it's a basic shape, a triangle, a circle, a semicircle, a square, we can use tables. And then we have composite areas also, which are these built up areas here, which are shapes that are made up of a bunch of little shapes that we know. And also, we can stitch together all those small shapes with their moments of inertia and figure out what the overall moment of inertia is for the overall shape. So those are the two different things. I guess it's three different things that we're doing. The very basic, using tables, we're going to do integration, and then we're going to do the composite area. So to think of some of the applications of area moment of inertia, let's say you have a plank of wood, a 2 by 10, so 2 inches wide and 10 inches tall, and it's 8 foot long board, and you lay it actually where it's 10 inches wide and 2 inches tall. So you lay it flatwise between two sawhorses, right? And it's 8 feet between the sawhorses or thereabouts. And you go up and you stand in the middle. Would that be bouncy? And I think you know it would be. Matter of fact, if you bounce on it too much, you might break it. If you were to rotate that board, though, 90 degrees, and obviously you'd have to have somebody holding the board from rolling over due to torsion. But so let's just say it's been stabilized and you stand on it on its side like this. Is it going to be less bouncy? Yeah, it's going to be a lot less bouncy. It's probably also going to be a lot stronger, be able to hold up a lot more load. And that's not because the wood grains are somehow magically different in one direction versus the other. They're actually the same. What's happening is the geometry of the board actually plays a role in how the board can resist those internal moments and shears that are acting in the board. So that's why it's so very important that we're going to calculate area moment of inertia for, again, not for statics, but the next step when you go to apply statics to other problem types. In addition to the strength and stability of solid structural members, the moment of inertia also has applications in fluid statics and buoyancy, like the moment of inertia. That's why a catamaran is more stable than a single hull boat, because the moment of inertia of the hull-water interface is greater for a catamaran. There are also many other applications. Moment of inertia, area moment of inertia, is all about, quantifying how far spread out the area of a cross-section is. So if you have more spread out, like the catamaran, they have two big pontoon, one hole and then another hole very far away, and that helps to stabilize it. You can't knock over a catamaran nearly as easy as you can, especially like a sailboat without a keel would just flip right over. Catamarans are much more helpful in fighting that overturning, and it's because of its area moment of inertia. Now, again, it might feel odd to switch to geometry and statics, but like I've been saying, this is going to be really important moving on to your future mechanics courses. So I have this blob of material here, just some generic cross-section, and then I've got a differential area here that I'm going to call dA. And it's located at some distance x from the origin and some distance y from the origin in the other direction. Okay. The moment of inertia, the area moment of inertia, is actually more correctly called the second moment of area. We call it moment of inertia. Think about it, it's kind of weird. We're talking about area and we're talking about inertia. I mean, inertia usually deals with mass. The reason we call it moment of inertia is because it's actually almost the identical concept to mass moment of inertia. It's just dealing with area as opposed to dealing with mass. The concepts are very similar. In many textbooks, they're covered in the same chapter. So, we usually say moment of inertia, even though we know the name is technically wrong. It's really second moment of area. Again, somebody might clarify and say, I'm talking about area moment of inertia. Even that's technically wrong because we're not dealing with inertia. We're dealing with area, but whatever. So when I say moment of inertia throughout these lecture slides, I'm talking about the area moment of inertia. The cool thing is now that once you know how to calculate this, you can apply it to those other ones, those other versions of moment of inertia really easily. All right, now moment of inertia is similar in some ways to the moment that you've already been working with in this class. We call it moment, right? Those the curvy vectors. Those curvy vectors are actually the moment of force, right? We call it the moment of force. Moment in engineering means, that taking something and multiplying it by a perpendicular distance. So a moment of force, we're taking that force and we're multiplying it by a perpendicular distance, and that would be the tendency for rotation, the moment of the force. So the second moment of area, if you guessed it, you actually multiply it by that perpendicular distance twice. So moment of inertia is going to be that distance, the perpendicular distance from the axis you're summing, you're calculating the moment of inertia about up to that, So here, if I was calculating the moment of inertia about the x-axis, it would be y times dA, or y squared dA, where dA is that differential area. If I'm finding the moment of inertia about the y-axis, it would be x squared dA. There's also the polar moment of inertia, which I'm not showing in here, but it would be like a radius out to this point, r squared dA. The moment of inertia Ix, like I just said, is going to be y squared dA. Here's it in more formal terms. This is an integral. It's technically a definite integral. You're going to be integrating over the area, right, of y squared dA, the area, the differential area there, right? If you're taking a distance and squaring it and then multiplying against it in area, so you're going to have length times length times length times length. So your usual unit's going to be like inches to the fourth or meters to the fourth or millimeters to the fourth or whatever, right? Length to the fourth power is what moment of inertia's units are. Another important note, the I for a shape about an axis going through the centroid of that shape will be the smallest moment of inertia for any axis parallel to that axis. Okay, so the x-axis that we're seeing here would not, if we move this x-axis up and somehow got to the centroid, which is probably right up here somewhere, right? That if we moved x-axis up there and called it the centroidal x-axis, when we calculated the moment of inertia about that axis, it would be at its smallest value. Think about it. The farther away the area is from the axis, the bigger the moment of inertia, y squared dA. So if you can get all of this area as close as possible to the axis, or move your axis as close as possible to the centroid, you're getting it as close as possible to all of the area. So you're reducing that moment of inertia down to its smallest value possible. The first way you're going to do moment of inertia, and this is actually probably, in the grand scheme of things, the most common way that people calculate moments of inertia. Because there's a lot of things in engineering is made of very basic shapes. We like to use very regular, squares, triangles, circles. And even when we make those composite areas, which is the last concept we're going to learn in this lecture, we usually make built-up shapes like that I-beam that you saw on the earlier slide out of a bunch of small rectangles. So we're going to use the tables. Even when we go to that last method, we still use this method. So this method is very common. Okay? You find a shape, you do it by, find the moment of inertia by integration, which is the second method I'm going to teach you. Once you've done it once, if you solve for it in symbolic values and not just numerical values, you would have the formula, right? So once it's been done, it's been done. So they can make tables that you can just plug values into and get the answers. So that's what this table method is. If you can match a picture in a table, and it will spit out the moment of inertia equation for you to use. And those tables are everywhere. You can find them all on the internet. Tons of websites have it. You can, if you have a statics textbook, it's going to be in there. The FE handbook, the reference guide you take when you take the FE exam, they're going to be in there. A whole table is full of different moments of inertia and centroids because they cover centroid in that same table. And those tables usually give the moment of inertia about the centroidal axis of the shape. Like for a square, it's going to give you BH cubed over 12, and that's going to be about the centroidal x-axis of that square, meaning through the center of the square. Why do they do that? Well, they have to give you about some axis, and the one that makes the most sense is the centroid. It makes the most sense for many reasons. One is all the other axes that they could pick would all be arbitrary. I mean, why would they pick one axis over the other? The center of it makes a lot of sense to pick. Remember, I also told you it is the smallest moment of inertia for any axis parallel to that axis. The cool thing about that is we have this concept called the parallel axis theorem that says once you know the moment of inertia about a centroidal axis, you can easily, by applying the parallel axis theorem, amplify that moment of inertia to make it be the moment of inertia that's about an axis parallel to that centroidal axis. It's just adding another term to your work. So you can look up the first term in your table and then just modify it to get the value that you need. So again, the parallel axis theorem states that starting with the moment of inertia about the centroidal axis, you can find the moment of inertia about any axis parallel to that axis by adding an additional term, AD squared. A is just the area of the shape, and D is the distance between those two parallel axes. Pretty simple, right? If you can find the table for your shape, this is by far the easiest method for doing this. The other two methods I'm going to show you are a little bit slower. This is really easy. The work has been done for you. You just have to have the table to look it up. You have to know the rules too. Look at the picture, follow the picture to the T. If you can find a picture that matches, then you get a moment of inertia as a formula. For instance, for a square, the moment of inertia I sub x. So x is this, see, this is through the centroid. C here is often centroid. I think the FE handbook does it the same way. A lot of textbooks and all will call the centroid C, and they'll show the axes coming out from there. This one also has this x prime axis down on the bottom edge. We'll get to that in a second. But the I sub x, the moment of inertia about this axis right here, is this formula. You can plug and chug. B times h cubed, so the width times the height cubed over 12. If you want to do the moment of inertia about the y-axis, guess what? It's the same formula, just now you got to turn your head 90 degrees to look at it. So now it's hb cubed over 12. What if I want the moment of inertia about x prime, though? Now I can use I sub x and apply the parallel axis theorem to it. Remember, I'm going to take this value and I'm going to add AD squared to it. What's A? B times H, the area in blue. What's D? D is the distance between the two axes, the shortest distance. So the distance between x to x prime is going to be h over 2. So I can easily just add, here's my AD squared term right here. So this first term, bh cubed over 12, is this one. That's from a table. This is one that I'm adding manually. The area times the distance between the two axes squared. I get, once I do the math and find, and simplify my fraction, I get bh cubed over 3. Now, a lot of manuals and reference tables will actually show this one as well, this bh cubed over 3. It's especially important for rectangles and squares because we will use that when we get into the integration version, because we'll use a rectangular element, and this is a rectangle. For a triangle, the formula would be bh cubed over 36 for a moment of inertia about the x. Again, the opposite for moment of inertia about the y. hb cubed over 36, just straight out of a table. For a circle, you have pi over 4 times r to the 4th, where r is your radius. Ix and Iy are equal to each other here because the circle is, what's x and what's y in a circle?